Today, I want to talk about loci on an Argand diagram or complex number plane when we're using moduli of complex numbers. Let's first look at this equation. Mod z minus 3 equals 2. What can you say about all possible positions of the point z where mod z minus 3 is 2? Or what is the locus of z such that mod z minus 3 is equals to 2? Remember that we can think of mod z minus w as the length of the vector wz, or sometimes it's better to think of it as the distance from w to z. Okay, with that idea, just think what this locus is. Just pause the video for a moment and think, what is that locus? Mod z minus 3 equals 2 means that the distance from 3, 0 to z is always 2. Well, if that's the case, we must have a circle, center 3, 0, and radius 2. And here it is. There we can see center 3, 0, radius 2. Okay, let's have another equation to look at. What happens if we start off with the equation mod z minus 5 is equal to mod z minus 1? How am I going to draw the locus on this diagram? Okay, stop the video again. And when you've solved that, then you can start up again. Well, this equation tells us that the distance from 5, 0 to z is equal to the distance from 1, 0 to z. So let's just mark those 2 points on the diagram. There's the point 1, 0, and there's the point 5, 0. And we're looking for the locus of all points which are the same distance from the 2 red dots. And this is just the perpendicular bisector of the line joining 1, 0 to 5, 0. Okay, we haven't stopped. What happens now if I look at this one? What am I going to draw on my diagram for this? Okay, once again, stop the video and think for yourself. What's actually going on? Here, we need to rewrite z minus 3 plus 4i as z minus brackets 3 minus 4i. This second line now tells us that the distance from 3 minus 4i, which is the point 3 minus 4, to z is always 5. So we have a circle, center 3 minus 4, radius 5. So our center is at 3 minus 4, around about there. What have I got to be careful about now? Do I just draw any old circle? It's a sketch after all. What am I thinking of here? Where's the origin? When I draw the circle, will the circle be outside the origin? Will the origin be outside the circle, or will the circle contain the origin? Or is neither of those true? The circle has radius 5, the center is at 3 minus 4, the distance from the center to the origin therefore is 5. So when you're drawing a circle, you must make sure that your circle is in the right place relevant to your origin. It either will be a circle which has the origin inside, or it'll be a circle and the origin is outside, or the circle will go through the origin. And so there it is. A circle, center at 3 minus 4, radius 5, will go out to 8 that way, back to minus 2 that way, minus 4 up to 1 there, and down to minus 9 there. Goes through the origin. Okay, one more. What can we say about this one? Well, now I think you're probably beginning to get the idea. We're looking first of all at z minus 2 minus I and z minus 1 plus I. And so the distance from 2 minus 1 to z must be the same as the distance from minus 1, 1 to z. In other words, we're looking for the locus which is equidistant from these two red points. Just the same idea as we had before, but a slightly more complicated. We need the perpendicular bisector, which is now at an angle to the axes. And here it is. But how can we find the equation of this line? That's the next problem. Well, we've got enough from P1, P2 work. We know where those 2 points are. One is the point 2 minus 1. The other one is the point minus 1, 1. And so we could work out the gradient of the green line, the gradient, therefore, of the perpendicular line. So we have the gradient of our locus. We could also work out the midpoint of our green line, and therefore we would have a point on that line. Not very difficult, but I think in this case, with complex numbers, it's just a little bit easier if we do it a slightly different way. Well, a very different way. If we think of z as the point x plus iy, then our equation becomes mod x plus iy minus 2 plus I equals mod x plus iy plus 1 minus I. Well, let's collect together the real parts and the imaginary parts. X minus 2, there's the real part, plus I times y plus 1, there's the imaginary part. That has to be equal to x plus 1 is the real part, plus I times y minus 1. We want those two moduli to be equal. Well, what is the modulus of a complex number? We just square the real part, square the imaginary part, add them, and then square root. Well, if we square both sides first, then we haven't got to worry about the square root. We've now got x minus 2 squared plus y plus 1 squared is x plus 1 squared plus y minus 1 squared. Okay, let's work that out. Easy algebra. X squared minus 4x plus 4 plus y squared plus 2y plus 1, x squared plus 2x plus 1 plus y squared minus 2y plus 1. X squared cancels with x squared, y squared cancels with y squared, and we're just left with 2y plus 2y is 4y, minus 4x, take away 2x from the other side, minus 6x, plus 5 minus 2 is plus 3. So there is the equation of our straight line. Is it sensible? Well, when y is 0, x is equal to a half. That's not bad. And when x is 0, y is equal to minus 3/4. So it looks as though we've got the right thing. Okay, let's look at this one. This says basically that the distance from 1 is twice the distance from 4. So we're looking for point Z, where the length of the red line is twice the length of the blue line. Let's have a look at this on autograph. Here, that looks as though it's a possibility. That doesn't look very good. That's certainly no good. Can we think of any points which must be true? The length of the red line has to be twice the length of the blue line. Well, if I come down to 3, then I've definitely got 1 to 3 is 2, 3 to 4 is 1. The length of the red line is twice the blue line. So there's one point. That looks feasible. That doesn't. That doesn't. Can we see another point which must be true? Oh, what happens if I come down here? 1 to 7, half the red line has disappeared, I'm afraid, but 1 to 7 is 6, and 4 to 7 is 3. So there is another possible point. So we've got lots of points in this sort of shape. I've come too far, about here. If I come too far over, the blue line is now longer than the red. So I've got to stay that side. So we are sort of going around like that. And anything we do above must be the same below by symmetry. So what shape do we think we might have between the two? Is it a circle? Is it an ellipse? Or is it something different? Well, that's, I think, where we now have to go and look at some algebra. Let's put z equal to x plus iy. Then the top equation becomes 2 mod x minus 4 plus iy is mod x minus 1 plus iy. Well, let's square both sides. 2 squared, mod squared, mod squared. That gives me 4. Real part squared, x minus 4 squared. Imaginary part squared, y squared. Real part squared plus imaginary part squared. Okay, let's work those out. We get 4 times x squared minus 4 times 8x plus 4 times 16 plus 4 times y squared. And that is x squared minus 2x plus 1 plus y squared. Subtracting x squared from both sides, 3x squared. Add 2x minus 30x. I'm going to subtract the 64 from both sides. That's going to give me minus 63. And I'm going to subtract y squared. That gives me plus 3y squared. I've done it like that because it makes the next lines look nicer. Common factor of 3. Did you notice that? X squared minus 10x plus y squared. Let's leave a little bit of a space there. And let's make that look like a plus, equals minus 21. Complete the square. Half of 10 is 5. Square it and add it, adding 25. That now gives us x minus 5 squared plus y squared is 4. Well, there we have a circle, center 5, radius 2. Let's go back to autograph and let's have a look. There I have drawn for you the circle, center 5, radius 2. And here is one of the points. It looks pretty good. The red line always looks twice as big as the blue line. Doesn't matter whether we're above or below, it's working well. So we've had a little proof there of this one in particular. This was quite nice arithmetically. We didn't get any fractions. You can easily end up with nasty fractions coming down here. If that happens to you, don't worry. So we started with 2 mod z minus 4 is mod z minus 1. We turned it into x minus 5 squared plus y squared is 2 squared. There is the circle, center 5, radius 2, and just 2 illustrations. This result is called Apollonius's circle. Apollonius was a Greek philosopher who lived about 2,200 years ago. He didn't certainly have the benefit of complex numbers, nor did he have the benefit of coordinate geometry. He proved this all by pure geometry. So whenever you get an equation which reads mod z minus 4, mod z minus 1, and something other than 1, then you've got Apollonius's circle. If you don't have a 2 there, then it would simply be the perpendicular bisector of the line joining 1 and 4. So if the number there is 1, or if there isn't a number, it's easy. If the number is not 1, then you must go through the algebra that we've just done to get the equation.